This is the video lesson for conservation of energy. The learning target for this lesson is, I am learning to describe the behavior of a system using conservation of mechanical energy principles. The success criteria for this lesson are, I can understand that mechanical energy is the sum of a system's kinetic and potential energies. I can understand that any change to a type of energy within a system must be balanced by an equivalent change of other types of energies within the system, or by a transfer of energy between the system and its surroundings. And I can understand that if the total energy of a system changes, that change will be equivalent to the energy transferred into or out of the system.
So let's talk about the conservation of energy. So if no external forces do work, then the change of energy, delta E, is equal to 0. So if delta K plus delta U, which is equivalent to delta E, equals 0, that means that delta K equals minus delta U. So the system can change potential energy for kinetic energy and vice versa, but the total mechanical energy always remains the same. So this is in the situation where we have no external forces doing work. In this example, where the plane is climbing, the change in kinetic energy is smaller than 0. So it's losing kinetic energy, but the change in potential energy is greater than 0. So it's gaining potential energy. So as the plane flies up, it's losing speed. So it's losing kinetic energy, but it's gaining potential energy because its height is increasing. And in the second example, since the plane is diving, the plane is gaining kinetic energy. So the change in kinetic energy is greater than 0, but it's losing altitude. So the change in potential energy is less than 0. So it's losing altitude, so its change in potential energy is going down while it's speeding up as it goes, so its change in kinetic energy is greater than 0. Okay, so continuing to look at conservation of energy. If only forces like gravity or spring are part of a system, its total mechanical energy stays the same. So total mechanical energy stays the same. So we call the force of gravity and the spring force conservative forces, because they don't change the total mechanical energy. We call those forces conservative forces. So if we look here at our ball dropping, we have the ball starts at y sub naught, or y naught, and it has an initial velocity of 0. So as it falls, when it reaches the height of y, it has a velocity v. And finally, when it falls all the way down to the ground at 0 height, it has a final velocity of v sub f. So we can look at our equations here. So the gravitational potential energy at the beginning at UG naught is equal to m times g times y naught, and our potential energy is 0 because our initial velocity is 0. At the middle point, u sub g, we have m times g times y, and our kinetic energy is 1/2 mv squared, because our velocity is just v. And then our final potential energy, UGF, is equal to 0 because our height is 0, and our kinetic energy, k sub f, is equal to 1/2 mvf squared because our final velocity is v sub f. But everywhere, at every point, the total mechanical energy, k plus u, is going to be a constant. Okay, so let's look at an example here. We have a 2-kilogram ball dropped from a height of 20 meters. What are its kinetic energy and its velocity when it's 5 meters above the ground? Okay, so we have This distance is 20 meters. And we want to know, as the ball drops, so when it reaches this height of 5 meters above the ground, what is velocity and kinetic energy? Okay, so the way we're going to figure this out is we are going to use conservation of energy. So we know that our total energy is equal to K plus U, which is UG. So we can say that our initial kinetic energy plus our initial gravitational energy is going to equal our kinetic energy at 5 meters plus our potential energy at 5 meters. So our potential kinetic energy at the beginning is equal to 0. And our potential energy at 5 meters is equal to mgy at 5 meters. So our kinetic energy is equal to mgy at 5 meters. So our kinetic energy at 5 meters plus the leftover potential energy at 5 meters. So let's figure out our potential energy at 20 meters. So we have our mass, 2 kilograms, times g, which is 10 meters per second squared, times our total height, 20 meters. That's going to equal 400 joules. Okay, so we have 400 joules on the left side of the equation. And on the right side of the equation, we have 1/2 times the mass, which is 2 kilograms, times v squared, plus we have 2 kilograms times 10 meters per second squared times 5 meters. So we have 1/2 times 2 is just equal to v squared. So we have 400 joules equals v squared plus 100 joules. So subtract the 100 joules from both sides. So we have 300 joules is equal to v squared. So take the square root. And we have v is equal to 17.3 meters per second. So our kinetic energy then is equal to 300 joules.
So let's talk for a minute about the advantage of using energy to calculate things rather than kinematics and forces. So we know how to describe the ball falling from a height with kinematics and forces. So how is using energy different? So when we're describing free-falling objects and straight ramps with forces, it's fairly straightforward because the forces are constant. So again, with a straight ramp or just something just dropping straight down, the forces are fairly constant. So that's pretty straightforward. But when we're talking about more complicated paths, so if you have a curved path, for example, using Newton's laws are more difficult because the forces are changing over time. So potential energy depends on location only. It does not depend on the path taken. So we can use potential energy to help us calculate things when we have these changing paths. So in the absence of non-conservative forces like friction, the final state of a system, so we're talking here about the final position, the final velocity, or the final energy, does not depend on the path taken to get there. So it doesn't matter that the ball rolling down this curved ramp is curved. All that matters is that it went from this point to this point. So we can use energy to figure out things like the velocity at the bottom of the ramp rather than using kinematics or forces, because in those situations, in this situation like this with a curved ramp, forces and kinematics would be difficult to use, whereas energy is much more straightforward. So as an example, we have these three different ramps. So we have a short ramp here, a little bit longer ramp here, and a longer ramp with a curve in it here for the third one. So notice that they're all at the same height, this 5-meter height here. So if friction is negligible, and if they all start with V naught equals 0, all three blocks are going to hit the ground at the same velocity. And that's true because they all start with the same potential energy. They all start with potential energy mgh. So when they hit the ground, assuming because friction is negligible, we can say that all of that potential energy is converted into kinetic energy, which means that they all have the same velocity. Okay, let's look at another example where we have a spring launches a 10-kilogram block along a frictionless track with a speed of 7 meters per second. We want to know how high the block will make it up the ramp at the end of the track. Okay, so we're going to use this position here where the spring has released the block as our initial point. So this is going to be K naught plus UE, so that's the elastic energy, naught. And then up here at this highest point, this is going to be our kinetic energy, final kinetic energy, plus our gravitational potential. Okay, and because we're using conservation of energy, these two things, these two positions are equivalent to each other. So we have K naught plus spring potential energy is equal to final kinetic energy plus gravitational potential energy. Okay, so our spring potential energy is 0. The spring has sprung. It has exerted all of the energy that it had to move the block to get it started going with its initial speed of 7 meters per second. And then at the end here, when the block is at its highest point, it has no kinetic energy. So all we're left with is kinetic energy. Initial kinetic energy is equal to the gravitational potential energy. So we have our initial kinetic energy. So that's equal to 1/2 times our mass, which is 10 kilograms, times our initial velocity, which is 7 meters per second. And that's squared. So remember that kinetic energy is 1/2 mv squared. And then we have on the right side of the equation gravitational potential energy, which remember gravitational potential energy is mgy. So our mass is again 10 kilograms. G, we're going to say, is 10 meters per second squared. And y is what we're looking for, which is, we're going to say, is h. So our masses divide out. So we're left with 7 squared, which is 49, divided by 2. So we have 24.5 meters squared per second squared on the left side. And we have 10 meters per second squared times h on the left side. So I'm going to move all this down below the problem.
Okay, so we're going to divide both sides by h, and that gives us a height of 2.45 meters. So notice that meters per second squared so meters squared per second squared is divided by meters per second squared, which leaves us just 1 unit of meters.
So what have we learned in this video? We've learned about mechanical energy. Mechanical energy, also called total mechanical energy, or just total energy, is the sum of an object's kinetic and potential energy. We've learned about the conservation of energy. If there is no external work done, changes to one type of energy must be balanced by a change in another type of energy. So a change of kinetic energy must be balanced by a change in potential energy, or vice versa. And we've learned about the advantage of using energy in certain types of problems. So potential energy depends on location, not path taken, and so makes solving certain types of problems easier. Thanks, everyone.